Welcome back to the deep dive. It is good to have you here. Today, we are shifting our mindset a little bit. Usually when we talk about pharmacology or even just, getting sick, we think about a skirmish.
Right. A quick fight.
You get a sore throat, you take a pill for a week, the bacteria die, you go on with your life. It's quick, it's decisive.
Exactly. It's a battle of maneuver. Fast in, fast out.
But today is completely different. We are not talking about a skirmish. We are talking about a siege.
Well, that's a good word for it.
We're talking about trench warfare. We're talking about the pharmacology of attrition.
It is a fitting metaphor, really. I mean, when you look at the history of infectious disease, few enemies have dug in deeper, held their ground longer, or frankly fought back with more biological stubbornness than the Mycobacteria.
And we are specifically looking at the titans of this genus today, tuberculosis and leprosy.
Diseases that have, and I'm quoting our source material directly here, terrorized humankind since antiquity. And I think there's a misconception we need to clear up right at the top. We tend to think of TB or leprosy as, Victorian-era problems.
Right, something from the Dickens novel, the tragic heroine coughing delicately into a handkerchief.
Or something even older, something from the Middle Ages. We've sort of relegated it to history.
We think of it as history, not as current medicine.
But the reality is just starkly different. I mean, tuberculosis, or TB, it remains the most important infectious killer of humans. Period.
Wow.
It's not a relic. It is not history. It is a massive, current, ongoing, global event.
That is such a heavy statement. The most important infectious killer. And, just when we thought we had the map for that fight figured out, the landscape started to shift. We have new nightmares emerging.
We do. We're seeing things like Mycobacterium abscessus. One of our sources, Goodman and Gilman, calls this a new antibiotic nightmare.
A nightmare? Why? What makes it so scary?
The reason is terrifyingly simple. It has what the book calls a universal propensity to develop drug resistance.
Universal propensity.
It's as if it's biologically designed to ignore our weapons. It learns to shrug them off almost immediately.
So the mission for this deep dive, then, is to understand how we fight an enemy like that. How do you lay siege to a fortress that is sealed so tight?
And a fortress that learns from your attacks.
Exactly. So for this discussion, we are going to be synthesizing two massive, really foundational sources. We've got the clinical clarity of Katzung and Trevor's Basic and Clinical Pharmacology, specifically their chapter on antimycobacterial drugs.
That's chapter 47, for those of you who are reading along in the recent editions.
And we are pairing that with the incredible molecular depth of Goodman and Gilman's The Pharmacological Basis of Therapeutics, which is chapter 60.
It's a really powerful combination. Katzung gives us the what and the how to. It's the clinical playbook, right? The dosages, the side effects, the regimens.
The practical guide.
The practical guide. But Goodman and Gilman, it gives us the why. It takes us deep down to the molecular level, looking at the atomic structures, the enzyme kinetics that make these drugs actually work, or in some cases fail.
And before we march into battle here, a really important disclaimer for everyone listening. This deep dive is a conceptual map. It's an interpretive synthesis to help you revise and really understand the landscape. It is absolutely not a substitute for the textbook.
100%. You cannot learn to perform surgery by listening to a podcast, and you really can't master pharmacology without looking at the data tables, the chemical structures yourself.
Right.
If you want medical mastery, you have to do the active reading of these chapters. We're here to build the scaffold for you. You have to be the one to lay the bricks.
Well said. So let's lay out the roadmap for today. What are the key takeaways, the big pillars we want you to walk away with?
I think we can boil it down to 5 pillars to hold up this whole discussion. First is biological stubbornness.
Okay.
You need to understand that we are fighting slow growth, a kind of waxy armor, and the fact that these things have hiding spots inside our own cells.
So the enemy has a serious home field advantage.
Precisely. The second pillar is combination necessity. We will literally do the math, the probability math, that shows why using one drug against active TB isn't just a bad idea, it's actually considered malpractice.
I love that part. The math is, it's terrifying, but it's also incredibly clear. It makes the whole strategy click.
It does. Third is duration logic. Why does treatment take months or even years? It's not arbitrary. It's a biological necessity.
Okay.
Fourth is toxicity vigilance. These drugs, they're not gentle. They tax the body, specifically the liver, the nerves, And the eyes. You have to know what to watch for because the cure absolutely comes with a cost.
And the fifth and final pillar.
That's the systems view. This isn't just about one patient and one doctor. Adherence isn't just about being a good patient. It's a pharmacological requirement to stop the evolution of superbugs that affect all of us.
A public health imperative baked into the pharmacology.
Exactly.
Okay, let's unpack this. Let's start with the enemy itself. Section 1, the fortress.
The fortress is absolutely the best way to visualize it.
So here's the thing that I think confuses people at first. When I get, say, strep throat or a simple sinus infection, I take penicillin or amoxicillin. In a few days, the bacteria pop, the immune system cleans up, and I feel great. Why is Mycobacterium so much harder to kill? What makes it so special?
It is all in the name. Mycobacterium. It comes from the Greek mycos, which means fungus.
Fungus. But it's bacterial.
It is, but the name refers to the waxy, almost fungus-like appearance of the colonies when they grow in a culture.
Yeah.
But that wax isn't just for show. It is a suit of armor.
Okay, so Katsung mentions this lipid-rich cell wall, but Goodman and Gilman really gets into the weeds on the molecular details here.
They do, and it is fascinating. The cell wall of a mycobacterium is more than 60% lipid.
60%.
Over 60%. Just think about that for a second. Most bacteria, like the strep you mentioned, they have these peptidoglycan walls. They're strong, but they're relatively porous. They're kind of like chain link fences. Drugs can slip through the gaps. But mycobacteria are wrapped in a layer that is 60% fat. It's like they've covered their chain link fence in layers and layers of tar.
And we are talking specifically about something called mycolic acids.
Yes. And these aren't your standard fatty acids that you'd find in a typical cell membrane. These things are massive molecules. We're talking about two-branched 3-hydroxy fatty acids with carbon chains that are 76 to 90 atoms long.
76 to 90 carbons. That is chemically enormous. I mean, a typical fatty acid in our bodies is, what, 16, 18 carbons?
Exactly. It's a whole different scale.
Yeah.
And what this creates is an intensely hydrophobic barrier. It's greasy, it's waxy. Goodman and Gilman calls it an extraordinary shield.
Yeah, shield.
It prevents most pharmacological compounds from even reaching the cell membrane or the cytosol. It's like trying to shoot an arrow through a tank. Many of our drugs, especially the water-soluble ones, literally bounce off because they just cannot penetrate that grease.
So the first problem is just getting in the door. But it's not just a passive wall, is it? It's not just that they have this thick skin. They are actively fighting back.
Correct. This is the second layer of their defense, what we can call the efflux problem.
Efflux, so pumping things out.
Pumping things out. Even if a drug molecule manages to, by chance, slip through that waxy armor, the bacteria have pumps waiting right there on the inside to grab it and spit it right back out.
I was shocked by the stat in the source material regarding this. It said that ABC permeases, which are a type of these transport proteins, these pumps, they comprise 2.5% of the entire Mycobacterium tuberculosis genome.
Isn't that staggering? It's a huge investment of genetic real estate. Imagine if 2.5% of your DNA was dedicated solely to building bouncers to throw people out of your house.
That's a great analogy.
That is how committed Mycobacterium is to keeping toxins out. They are genetically wired from the ground up to reject our treatments.
So we have the waxy wall, we have the bouncers pumping drugs out, and then there's the third piece of this fortress strategy. The location. They don't just float around in the blood where our immune cells can get to them easily, do they?
No, they are much smarter than that. They play hide and seek, and they hide inside the patient's own macrophages.
Wait, they hide inside the very cells that are supposed to find them and kill them?
Exactly. They turn the prison into a sanctuary. It's a brilliant evolutionary move.
How did they do that? I thought a macrophage was supposed to just eat them and digest them?
Normally, yes. When a macrophage engulfs a bacterium, it puts it in this little bubble called a phagosome. Then it's supposed to fuse that phagosome with another bubble full of acid and digestive enzymes called the lysosome.
Right, the phagolysosome, the cellular stomach.
Precisely. But mycobacteria have evolved mechanisms to prevent that fusion. They basically jam the machinery. So they just sit there, safe and sound inside the phagosome, protected from the rest of the immune system.
And protected from our drugs.
And protected from our drugs. This creates a massive physicochemical barrier. For a drug to work, it first has to cross the patient's own cell membrane to get into the macrophage.
Okay, step one.
Then it has to navigate the macrophage's cytoplasm and enter the phagosome where the bug is hiding.
Step two.
And only then, after all that, does it finally have to get through the bacterium's 60% lipid, waxy wall. It is a logistical nightmare for drug delivery.
So many layers. And there is one more factor, one more piece of this biological stubbornness that makes this a war of attrition, and that is time.
Yes, the growth rate. We classify mycobacteria into rapid growers and slow growers. The rapid growers, like abscesses, are visible in a culture in less than 7 days. But the slow growers, the ones that cause TB and MAC, or Mycobacterium avium complex, they take much, much longer. Weeks, sometimes.
And counterintuitively, being slow is a huge advantage when you're fighting antibiotic.
It is a massive advantage. Most of our best antibiotics, like the beta-lactams, target the machinery of cell division. They attack when a cell is actively building a new wall or copying its DNA.
They hit a moving target.
They hit a moving target. If the cell is dormant or just sitting there metabolizing and growing incredibly slowly, the drug has no target. It's like trying to bomb a factory that's been shut down for the holidays. You can drop all the bombs you want, but if the machinery isn't running, you're not actually disrupting the process.
That explains so much. That's why Katzung really emphasizes that the response to chemotherapy is slow. We were looking at months, sometimes years of treatment because we are essentially just waiting. We're waiting for the bacteria to wake up and make a mistake so we can kill it.
Precisely. We are laying siege, and we're waiting for them to peek their heads over the battlements so we can finally attack.
Okay, so let's put that together. The enemy is heavily armored, they're hiding in our own cells, they're actively pumping our weapons out, and they're moving incredibly slowly.
A formidable foe.
Which leads us directly to Section 2, the logic of combination therapy. You mentioned earlier, and I think this is so critical, that monotherapy using just one drug is considered malpractice.
It absolutely is. And it's not a matter of opinion. It comes down to the cold, hard math of resistance. It is a pure numbers game.
Okay, walk us through the math. Let's make this concrete.
So in any large population of Mycobacterium tuberculosis, there are going to be spontaneous mutations. Nature makes mistakes when it copies DNA. It's just a fact of life. The rate of spontaneous mutation that confers resistance to a single drug, like isoniazid, is roughly 1 in 10 to the 6. 1 in a million.
1 in a million. That sounds pretty rare. I mean, if I had a 1 in a million chance of winning the lottery, I would not be quitting my job.
It sounds rare until you look at the clinical reality of the bacterial load. A typical cavitary lesion in a TB patient's lung, just one of those holes you see on a chest x-ray, contains about 10 to the 8 to 10 to the 9 bacilli.
So 100 million to a billion bacteria in one spot.
Right. So now let's do the math. If you have a billion bacteria, that's 10 to the 9. And the rate of resistance is 1 in a million, 10 to the 6.
Okay, so 10 to the 9 divided by 10 to the 6. That's 10 to the 3. 1,000.
1,000. You have, on average, 1,000 bacteria in that single lung lesion that are already, from birth, naturally resistant to drug A. They exist before you even give the first dose.
So if I treat that patient with just drug A, I kill the other 999,999,000 susceptible ones. The patient probably feels better initially, right? Their fever goes down.
They feel much better. The cough improves. But those 1,000 resistant bacteria survive?
And now they have no competition.
None at all. They had the whole playground to themselves, all the nutrients, all the space, so they replicate. And very quickly, the patient relapses. But now they have an infection that is 100% resistant to drug A.
You've artificially selected for resistance. You've essentially bred a superbug inside the patient.
You've run natural selection in fast forward. It's an iatrogenic disaster.
So how does adding a second drug fix this? How does that change the math?
We rely on the principle of independent mechanisms of action. If the probability of a bacterium being spontaneously resistant to drug A is 10 to the minus 6,
1 in a million.
And the probability of it being resistant to drug B, which works by a totally different mechanism, is also 10 to the minus 6.
Okay.
Then the probability of a single bacterium being resistant to both drugs simultaneously is the product of those two independent probabilities.
So you multiply them. 10 to the 6 times 10 to the 6.
Which is 10 to the 12, 1 in a trillion.
1 in a trillion. And we only have a billion bacteria in the lesion.
So the statistical likelihood of a pre-existing double mutant even existing is effectively 0. It's less than 1 bacterium. The odds are so vanishingly small we can basically ignore it.
That is the aha moment right there. That is why we never, ever treat active TB with a single drug. It's not just about hitting them harder. It's about covering all the statistical bases.
It is the absolute cornerstone of modern TB pharmacology. You use multiple drugs with different mechanisms to ensure that if a rare mutant manages to survive one drug, the second or the third or the fourth one will kill it.
It's a safety net built on probability.
A very effective one.
So let's look at the weapons we use in this combination. This brings us to Section 3, the first-line arsenal. The mnemonic that every medical student learns is RIPE. RIPE.
Rifampin, isoniazid, pyrazinamide, and ethambutol.
The big four. These are the drugs that have saved millions upon millions of lives.
The pillars of therapy.
Let's start with the I in RPE, because historically and clinically, it's a real heavyweight. Isoniazid or INH.
Isoniazid is a fascinating drug because it functions as a Trojan horse.
A Trojan horse.
Yes, it's a prodrug.
Yeah.
That means when it first enters the bacterium, it's completely harmless. It's inert.
So it has to be activated by something inside the bacterium.
Exactly. It requires a specific mycobacterial enzyme called CatG. That stands for catalase peroxidase.
Yeah.
The bacteria itself must possess this enzyme to turn the harmless isoniazid molecule into a deadly poison.
That's almost poetic, isn't it? The bacteria's own machinery is its undoing.
It is. The bacteria's metabolism becomes the trigger for its own death. So CatG activates INH. What happens next?
Right. What's the actual killing mechanism?
The activated form of isoniazid doesn't just float around. It forms a covalent bond, a really strong, irreversible bond, with a couple of key proteins, specifically ACPM and CUSA.
Okay.
This new, larger complex then jams up the works of a critical metabolic pathway. Specifically, it blocks the synthesis of mycolic acids.
Ah, we are right back to the wall, the fortress.
We are attacking the fortress walls. By inhibiting key enzymes like INWA-A, which is an enoyl acyl carrier protein reductase, isoniazid prevents the bacteria from building that 60% lipid shield.
So it's like a saboteur getting inside the castle and destroying the quarry where they get the stone to build the walls.
That's a perfect analogy. If you
Yep.
can't build the wall, you can't maintain the fortress, and eventually it crumbles.
But since it relies on the bacteria to activate it, I'm guessing that resistance has something to do with that activation step?
That's exactly right. The most common mechanism of high-level resistance to isoniazid is a simple deletion of the CatG gene.
It just gets rid of it.
The bacteria essentially figures out, hey, this catalase peroxidase enzyme is opening the door for the enemy, so through selective pressure, the mutants that have lost that gene are the ones that survive. If you can't make CatG, the Trojan horse never gets unpacked. The drug remains a harmless prodrug.
Just brilliant from the bacterium's perspective. Now, there is a human genetic component to isoniazid too, right? We have to look at the host, not just the bug. Something about acetylation.
Yes, this is a classic textbook example of pharmacogenetics. Humans metabolize isoniazid in the liver, and the main pathway is acetylation, which is carried out by an enzyme called N-acetyltransferase 2, or NAT2.
Okay.
But the efficiency of this NAT2 enzyme varies wildly across the human population. It's a genetic polymorphism.
And this gives us the fast acetylators and slow acetylators.
Correct. And it's not a small difference. Fast acetylators clear the drug really quickly. The half-life is about 1 hour. But in slow acetylators, the half-life is around 3 hours.
3 times as long. Does that actually matter for the patient, or is it just a lab value? Do we dose differently?
It's a great question. In practice, for TB treatment, the standard dosing regimens are designed to be effective for both. But where it really matters is in toxicity. The slow acetylators are significantly more prone to developing adverse effects
Why is that?
because the drug and its metabolites just hang around longer at higher concentrations. The total exposure over time is greater. And the toxicity profile of isoniazid is something every single clinician needs to have memorized.
This is where I have my own little mnemonic. I call it the drug that breaks the wall but steals your vitamins.
That is a very good way to put it. The most famous toxicity is peripheral neuropathy, and it's directly related to vitamin B6, which is pyridoxine.
How does it do that?
Isoniazid itself, or its metabolites, can react with pyridoxal phosphate, the active form of B6. It forms something called a hydrazone, which is then easily excreted in the urine. It literally strips the B6 out of your body.
And what happens when you run out of B6? I know it's crucial for nerve function.
It is. So patients start to develop peripheral neuropathy. They'll report tingling, numbness, a pins and needles sensation, or even burning pain, usually in the hands and feet. A classic stocking glove distribution. It can happen in about 10 to 20% of patients if you're using higher doses.
But the good news is it's almost entirely preventable.
Completely preventable. It's standard practice. If you prescribe INH, you prescribe 10 to 50 milligrams of pyridoxine a day along with it. It's a very simple, very cheap fix for what could be a very serious side effect.
But there is a darker side to INH toxicity, and that's hepatotoxicity, liver damage.
Yes.
And this isn't just a mild elevation of liver enzymes on a blood test. This can be full-blown clinical hepatitis.
It can be fatal in rare cases.
Mm.
And what's interesting is that the risk is clearly age-related. It's very rare in patients under the age of 20. But the risk starts to climb, and our text mentioned a specific threshold of around age 42, where the risk of serious hepatotoxicity goes up significantly.
And I assume it's worse for people who drink alcohol regularly.
Of course. Alcohol is also a liver toxin, and it induces some of the same enzymes. You're compounding the damage, so you have to monitor liver function tests, especially in older patients or those with pre-existing liver conditions.
So for isoniazid, breaks the wall, needs Cat G to work, watch the layer, and always give B6.
That's a summary.
Correct.
Let's move to the R in RPE,
Yeah.
the rifamycins, and the prototype here is rifampin.
Rifampin is the heavy artillery. If isoniazid is the saboteur breaking down the walls, rifampin goes straight for the command center.
Okay, what's its target?
It binds to the beta subunit of the bacterial DNA-dependent RNA polymerase.
That's a mouthful. Let's simplify that.
Okay.
RNA polymerase is the enzyme that reads DNA and makes an RNA copy.
Exactly. It's the cell's photocopier. Rifampin binds to the copier and jams it. Specifically, it targets the protein encoded by the RPB gene.
So if you can't make RNA,
You can't make proteins. If you can't make proteins, the cell's machinery grinds to a halt. The cell collapses. It is a powerfully bactericidal drug. It kills them dead. And what I found really interesting in the text is that rifampin is exceptionally good at penetrating tissues.
that is its superpower. It gets everywhere. It penetrates those phagocytic cells, those macrophages where the bugs are hiding. It gets into the caseous or cheesy material in the center of lung cavities. It hunts the bacteria down wherever they live, which isoniazid sometimes struggles to do as effectively.
But it comes with a very colorful warning label.
The orange warning, yes. Rifampin and its metabolites are a distinct reddish-orange color, and it will color all of your bodily fluids, urine, sweat, saliva, and most famously, tears.
I have heard stories from residents about patients calling the hospital in a panic, thinking they are bleeding to death internally because their urine has turned bright red or orange.
It can be incredibly terrifying if you aren't warned ahead of time, and a very specific clinical pearl. If your patient wears soft contact lenses, rifampin will permanently stain them orange.
Permanently.
Permanently. You have to tell them to switch to glasses for the duration of therapy, or they will be very, very unhappy with you.
Good to know. But beyond the color, rifampin is famous, or maybe infamous, for something else it does in the liver. It plays a pretty aggressive game with other drugs.
Oh, it is the Godzilla of enzyme induction. It is a potent, powerful inducer of a wide range of cytochrome P450 enzymes.
Which means it makes the liver chew up other drugs much, much faster.
Much faster. And this is a clinical nightmare for managing drug interactions. If a patient is on an anticoagulant like warfarin, rifampin will chew through it, their INR will drop, and their blood could clot when it shouldn't.
What about, say, contraceptives?
A huge one. If a woman is on oral contraceptives, rifampin will lower the effective dose of the hormones, and she could become pregnant. It's a known cause of contraceptive failure.
And maybe, most crucially for this particular patient population, HIV medications.
This is the big one. TB and HIV often go hand in hand. It's a devastating syndemic. Rifampin will dramatically reduce the levels of many protease inhibitors and non-nucleoside reverse transcriptase inhibitors.
So you could be treating the TB effectively, but the patient's HIV could break through their antiretroviral therapy because rifampin is clearing their other meds too quickly.
It's a major clinical challenge. It's like trying to put out a fire in the living room while another one starts in the kitchen.
That seems like a massive problem. Do we have a workaround for that?
We do, thankfully. We have other drugs in the rifamycin class. The most important one here is rifabutin.
Rifabutin.
It's structurally very similar to rifampin. It has the same mechanism of action, but it is a much less potent P450 inducer. So if you have a patient on a complex HIV regimen with protease inhibitors, we often swap out the rifampin for rifabutin to avoid those dangerous interactions.
Got it. So rifampin is the RNA jammer with the orange tears and the drug interactions. Now let's talk about the P, pyrazinamide or PZA.
PZA is the special ops agent of the group. It has a very, very specific niche. We use it primarily in the first 2 months of the standard 6-month therapy.
Why just the first 2 months? Why not for the whole duration?
Because it is what we call a sterilizing agent. We'll get into that term more later, but the short answer is that PZA allows us to shorten the total duration of therapy from what used to be 9 or 12 months down to just 6 months. Without PZA, the treatment has to be much longer.
How does it do that? How does it shorten the time? What is it doing that the others aren't?
It hunts the quiet ones, the sleepers. PZA is only active in an acidic environment, specifically a pH of around 5.5.
And where in the body do we find that kind of acidity?
Inside the lysosomes and phagocytosomes of the macrophages.
Ah.
That is exactly where the dormant, non-replicating, persistent bacilli are thought to be hiding out. Most of our other drugs can't work well in that acid bath, or they don't work well against non-growing bugs. PZA thrives in it.
So it's another prodrug.
It is, just like isoniazid. It gets taken up by the bacterium and is converted by an enzyme called pyrazinamidase, which is encoded by the PNCA gene into its active form, which is pyrazinoic acid.
Okay, and what does the acid do?
The current thinking is that it disrupts the bacterial cell membrane metabolism and transport functions. It essentially acidifies the cytoplasm of the bacterium from the inside out and collapses its ability to generate energy. It kills them in their hideout.
So it hits the dormant bugs in their acid bunkers, but like all the others, it has a cost. There's a toxicity profile.
The liver again. Hepatotoxicity. In fact, if you're looking at liver toxicity, PZA is often considered the most toxic of the first-line drugs. If a patient's liver enzymes start to spike during the first couple of months, PZA is often the first drug you'd suspect and stop.
Is there anything else?
Yes. We also see hypouricemia pretty consistently.
High uric acid in the blood.
Right. It inhibits the excretion of urate in the kidneys. For most people, this is just an asymptomatic lab finding. But in patients who are susceptible, it can provoke a painful attack of gout.
Okay, so that's PZA. Now the last of the first line, ethambutol, the E in IPE.
Ethambutol is the support player. It's often described as bacteriostatic at standard doses, not bactericidal. Its main job is to prevent resistance to the other drugs.
And what's its mechanism?
It inhibits an enzyme called arabinosyl transferase.
Let's unpack that. Arabinosyl transferase.
These are enzymes that are encoded by the MCA-B operon, and their job is to help build a key component of the mycobacterial cell wall called arabinogalactan.
So it's another wall drug, like isoniazid.
It is. It disrupts the structural integrity of the bacterium. It keeps the wall weak and more permeable, which may help the other drugs penetrate better.
The toxicity here is very specific, and it's quite scary. It's not the liver this time, it's the eyes.
Yes, this is the one you have to remember for exams and for clinical practice. The classic toxicity is retrobulbar neuritis.
Neuritis, so inflammation of the optic nerve. What does that look like for the patient?
Patients can experience a loss of visual acuity, a general blurring of vision, but the classic, almost pathognomonic sign is a loss of red-green color discrimination.
That is wild. You mean like suddenly a traffic light just looks all the same color?
Exactly. Or they can't distinguish the numbers in one of those Ishihara color blindness tests. It's very clearly dose-dependent. The risk is significantly higher at a dose of 25 milligrams per kilogram compared to the more standard 15 milligrams per kilogram.
So if you are prescribing ethambutol, you absolutely need a baseline eye exam.
You must. It's the standard of care. You have to test visual acuity and color discrimination before you start the drug, and you should check it monthly during therapy. If a patient reports any vision changes at all, you stop the drug immediately.
And does it get better?
Usually, the visual changes are reversible if you catch them early and stop the drug.
Yeah.
But if you miss it and keep dosing, the blindness can become permanent.
So that's our RIPE regimen. Isoniazid breaks the wall and steals B6. Rifampin jams the RNA and turns you orange. Pyrazinamide acidifies the hideout and can hurt the liver. And ethambutol weakens the wall but can mess with your eyes.
That is a perfect summary of the first-line arsenal. That combination, taken faithfully for 6 months, will cure the vast majority of drug-susceptible TB cases.
But sometimes it doesn't. Sometimes the wall holds. Sometimes the bacteria are already resistant to our best drugs, rifampin and isoniazid.
And that's when we get into MDR-TB, multi-drug-resistant TB.
Which brings us to Section 4, the second line and the new agents.
When the first-line drugs fail, we enter a much, much more difficult landscape. The second-line drugs are, as a rule, more toxic, less effective. They often require painful daily injections, and the treatment goes on for much longer, maybe 18 to 24 months.
The cure rate drops, the cost skyrockets, a total disaster.
A public health nightmare.
Let's talk about the fluoroquinolones first. Drugs like moxifloxacin and levofloxacin. We usually think of these for things like pneumonia or urinary tract infections.
They are DNA gyrase inhibitors. They stop the bacterial DNA from being properly coiled and uncoiled during replication. In the world of TB, they are absolutely critical for treating MDR-TB. In fact, they form the backbone of pretty much any modern MDR regimen.
So they're that important.
If your patient's strain of TB is resistant to the fluoroquinolones, their prognosis drops significantly. Losing the quinolones is a major blow.
But there is a huge caveat here regarding resistance, isn't there?
A huge one. Resistance to fluoroquinolones develops rapidly. A single point mutation in the gyrase, a subunit, is all it takes. This is why it is so dangerous to treat what you think is a community-acquired pneumonia with a quinolone if it might actually be TB.
Because you'll make the patient feel better temporarily.
But you'll be breeding quinolone resistance. You will have taken one of our best weapons against MDR-TV and thrown it away. You burn the bridge.
Then we have the older drugs, the injectables, the aminoglycosides like streptomycin or amikacin.
Streptomycin was actually the very first drug found to be effective against TB back in the 1940s. These all work by inhibiting protein synthesis at the 30S ribosomal subunit. They are powerful bactericidal agents.
But the toxicity is brutal.
Absolutely brutal. We're talking about significant ototoxicity. That's hearing loss and vertigo and nephrotoxicity, which is kidney damage.
Imagine being on a drug for months and months that is slowly, irreversibly taking away your hearing.
It is a terrible trade-off. We can save your life from this infection, but you might go deaf in the process. But for some patients with highly resistant TB, it's the only option they have.
However, there is hope on the horizon. We have some new guard drugs, and this is actually really exciting because for a long time, decades, really there was almost no new drug development for TB.
The pipeline was completely dry.
Now we have bedaquiline.
Bedaquiline is a true game changer. It was the first drug from a completely new class to be approved for TB in over 40 years. It's in a class called the diaryl quinolines.
And it has a totally novel mechanism, right? It targets the cell's energy factory.
It targets ATP synthase. Specifically, it binds to subunit C of the proton pump component of the ATP synthase. It literally starves the bacteria of energy, turns off the lights. Because mycobacteria are aerobic and rely heavily on oxidative phosphorylation, this is an incredibly effective way to kill them.
And then we have another new class, the nitroimidazoles, pretomanid, and delamanid.
These are fascinating because they seem to be specifically designed to kill the sleepers.
The dormant, persistent bacteria.
Exactly. They're also prodrugs, and they're activated by a special diazoflavin cofactor called F420, which is unique to Mycobacteria. Once activated, they have a dual action.
What's the first action?
They inhibit mycolic acid synthesis, so they hit the cell wall. But the really cool part is their second action. They also generate reactive nitrogen species, essentially nitric oxide.
So they gas the bacteria from the inside?
Effectively, yes.
Yeah.
And this burst of reactive nitrogen is thought to be what allows them to kill non-replicating dormant bacilli. This is huge because killing those dormant bugs is the key to shortening therapy and preventing relapse later on.
It's amazing to see these new, clever mechanisms being developed after so many years of stagnation. But TD isn't the only mycobacterial fight we're in. Section 5 covers special campaigns. Let's talk about MAC, Mycobacterium avium complex.
This is a completely different clinical context. We don't usually see disseminated massa disease in people with healthy immune systems. We see it in late-stage AIDS, when the immune system has collapsed and the patient's CD4 T-cell count drops below 50.
The body's walls are down.
Exactly. MAC-C organisms are everywhere in the environment, in soil, in water, but they're opportunistic. They only attack when the body's defenses are completely gone. And importantly, they are naturally much less susceptible to our standard TB drugs. The barrier to treatment is higher from the start.
So what's the strategy? We can't use RIPE.
We can't. The backbone of any MAC treatment regimen is a macrolide, usually clarithromycin or azithromycin.
Okay.
Then, to prevent resistance to the macrolide, we add at least one other drug, typically ethambutol, and often a rifamycin as well.
Rifampin or rifabutin?
Usually rifabutin. Again, because these patients are almost always on complex HIV medications, and rifabutin plays much nicer with those drugs than rifampin does. We need to treat the MAC without compromising the HIV treatment.
And we also use prophylaxis, right? We try to prevent it from happening in the first place.
Yes, that's critical. If an HIV patient's CD4 count drops below 50, standard guidelines recommend we start them on weekly azithromycin or daily clarithromycin as prophylaxis to prevent the infection from ever taking hold.
Now, let's pivot to the other ancient enemy we mentioned at the start, leprosy or Hansen's disease.
The organism here is Mycobacterium leprae. And here is a fun fact from the source material that has always stuck with me.
Yeah.
You cannot grow M. leprae in vitro. You can't just put it in a petri dish with some agar and have it grow.
So how on earth do we study it? How do we test new drugs against it?
In mouse foot pads.
You're kidding. Mouse foot pads.
That is the standard laboratory model for decades. We grow the organism in the foot pads of mice. It also grows naturally in 9-banded armadillos. But for routine lab testing, it's mouse foot pads.
That is incredibly specific. I have to assume it's related to temperature.
That's exactly right. M. leprae prefers cooler temperatures, which is why in humans it primarily affects the skin, the nose, the peripheral nerves, the testes, the cooler parts of the body. And apparently, mouse foot pads.
So how do we treat it? I'm guessing it's another combination regimen.
Always a combination to prevent resistance. The historical mainstay is a drug called dapsone.
Dapsone. That sounds like a sulfa drug.
It's structurally related and works the same way. It's an inhibitor of folate synthesis. Specifically, it blocks the enzyme dihydroapteroid synthase, just like sulfonamides do in other bacteria. By starving the bacterium of folate, you prevent it from making DNA.
And we pair that with rifampin.
Yes, rifampin is the heavy hitter here, too.
Yes.
It is incredibly effective against leprosy. The organism grows so unbelievably slowly, a doubling time of like 2 weeks, that even a single observed monthly dose of 600 milligrams of rifampin can be highly effective as part of the combination.
But there's a third drug, clofazimine, that has one of the most distinct and frankly socially difficult side effects in all of pharmacology.
Clofazimine is a phenazine dye. We still aren't 100% sure of its exact mechanism. Maybe it's membrane disruption, maybe it has to do with phospholipase inhibition, but we know what it does to the patient. It's stored in the reticuloendothelial tissues and, most visibly, in the skin.
And because it's a dye.
It causes a profound reddish-black discoloration of the skin and the conjunctivae.
Just imagine that situation for a moment. You are being treated for leprosy, a disease that for millennia has carried an immense, unfair social stigma and fear. And the very drug that is curing you is turning your skin a reddish-black color, marking you even further.
It can lead to severe depression and further social isolation. And because the drug is stored in fat and tissues, it has an enormous half-life around 2 months. Even after you stop taking the drug, it takes a very long time for it to wash out of your system. The discoloration can linger for months or even years.
That is just a heavy, heavy burden for a patient to bear. Which brings us perfectly to our final section, Section 6. Clinical integration and systems thinking. We've talked about all these individual drugs, but how do we put this all together in the real world?
Well, one key concept we have to distinguish between is sterilizing activity versus bactericidal activity. It sounds like a semantic point, but it's clinically very important.
Okay, break that down for us.
Isoniazid is our most powerfully bactericidal drug. It is fantastic at killing the rapidly growing bacteria, the active army, in the early phase of treatment. It knocks the bacterial count down quickly, which is what makes the patient non-infectious to others.
But that leaves the sleepers, the dormant ones.
Exactly. That is where our sterilizing agents come in. That's primarily rifampin and pyrazinamide. Their main job is to mop up the dormant, persistent bacteria, the ones hiding in the acidic environment of the macrophages or in the low-oxygen environment of caseous necrosis. They are the ones that prevent relapse months or years down the road.
So you need both. You need the initial assault to win the battle and the long-term cleanup to win the war.
You absolutely need both. That's why the RIPE regimen is structured the way it is.
And because this cleanup takes so long, 6 months is a long time to take multiple pills every single day, we run into the human element, the problem of adherence.
And this is where we have to state it plainly. In TB treatment, adherence is pharmacology. If a patient takes their medication sporadically, if they miss doses, they're creating the perfect training camp for drug resistance right inside their own lungs.
Budman and Gilman has this great description of it. They call it the arrow of time model of developing resistance.
Yes. It's a fantastic way to visualize the inevitable sequence of events. It starts with poor dosing, which leads to subtherapeutic drug concentrations.
The levels are too low to kill everything.
Right. And this non-lethal pressure triggers the induction of those iflux pumps we talked about. The bacteria start pumping the drug out harder. This increased survival gives them more time and more opportunities to develop random chromosomal mutations in the drug's target gene.
And eventually, you get a mutation that confers high-level resistance.
Yeah, now you have fixed high-level resistance. It's a slippery slope that starts with, oh, I forgot my pill on Tuesday.
Which is why we have DOT, directly observed therapy.
Yes.
And this isn't just a friendly suggestion, is it?
No. In most public health programs for TB, it is a requirement. It is the standard of care. It means a healthcare worker or another designated individual literally watches the patient swallow every single dose of their medication.
It sounds intrusive, even authoritarian.
It can feel that way, but you have to understand the stakes. When the alternative is the creation of a new strain of multi-drug-resistant TB, an airborne superbug that can kill up to 50% of the people it infects, then ensuring that the pills are swallowed becomes a fundamental medical and public health necessity.
It connects right back to your siege metaphor. You can't just leave the siege lines unmanned for a weekend and hope for the best.
Exactly. The pressure must be constant and unrelenting. If you lift the siege, even for a day, the enemy resupplies, rebuilds the wall, and you've lost ground.
So we have covered a lot of ground today. Let's do a quick synthesis recap, the REPE framework one last time.
Isoniazid, the wall breaker. Remember the key toxicities.
Yeah.
Neuropathies always give B6, and hepatotoxicity.
The RNA jammer, remember the orange fluids and the powerful P450 drug interactions.
The acid specialist. It's the sterilizing agent that kills the sleepers. Watch for uric acid and, again, liver toxicity.
The support player weakens the wall, and you must watch the eyes for red-green color blindness.
And the overarching logic.
Right.
Biological stubbornness from the Mycobacteria requires combination therapy from us and a long duration of treatment.
And never forget the systems view. Treating one patient's TB is about protecting the entire population.
So here's where it gets really interesting for me. The provocative thought to leave you all with as you go back to the textbooks.
Oh.
We talked about how some of the new drugs like predominid generate nitric oxide to kill the dormant bugs. They essentially poison them in their sleep.
Yes.
But I wonder, does the future of TB therapy lie not in poisoning their sleep, but in waking them up?
That is a fascinating and very active area of research. There's a concept of using resuscitation factors. These are molecules that could artificially wake up the dormant bacteria.
You trick them into thinking the coast is clear and it's time to start growing again.
Exactly. And the moment they start to replicate, they become instantly susceptible to our standard, cheap, powerful drugs like isoniazid.
So instead of trying to hunt them down in the dark with special weapons, you just turn on all the lights and make them come out into the open.
It's a brilliant strategy, in theory, but it is incredibly risky. If you wake them all up and you don't kill them fast enough, you have just massively exacerbated the disease. You've converted a latent, contained infection into a raging, active one. It is a very high-stakes gamble.
And then there's the other side of that coin, M. abscessus, the nightmare strain we started with.
That is the sober reality check. While we're developing these clever new strategies, the bacteria are evolving too, and we are seeing strains of non-tuberculous mycobacteria that resist everything we throw at them.
So what do you do then?
We might be entering a post-antibiotic era for some of these mycobacteria, where our only options are things like aggressive surgery to physically cut out the infected lung tissue, or even experimental therapies like bacteriophages. Viruses that are engineered to eat bacteria because our chemical drugs simply don't work anymore.
It is a war of attrition indeed, and the war is definitely not over.
Not by a long shot.
For those of you listening, if you want to really nail down the dosage tables, the resistance frequencies, and the molecular diagrams, you have to go back to the source. Read Katzung chapter 47. Read Goodman and Gilman chapter 60.
These frameworks we've discussed today are the skeleton. The real meat is in the reading. The reading provides the muscle.
Thanks for diving deep with us. Keep learning, stay curious, and maybe take your vitamin B6.
Always good advice.
See you next time.